Thank you very much. Thank you very much for that kind introduction, and also for everyone for coming.
Roger, nice to see you, Roger. And also be talking about advances in chemical analysis revealing insights into steroid hormone biology. Thank you, Ruth.
Thank you very much for that kind introduction, and also for everyone for coming today to listen. I was born in a small town called Barrhead on the west coast of Scotland, and here are my parents. My dad was in the RAF as a plane engineer, and he fought in the North African campaigns in World War II. When he left the RAF, he became an overseer in the car plants in Linwood and Paisley, that was Chrysler, and he made Hillman Imps. But there were mass redundancies there in the 70s. In his later years, he was the janitor in our local technical college and high school. And one of my early memories of my dad's job was on election days, where the voting would take place in his school, and he used to bring me home at the end of the day all the little voting pencils so that I could put them in my pencil case for school, which was really exciting when you were 8. My mum was a butcher's daughter, and here's my granddad's butcher shop in Pollokshaws Road in Glasgow. She went to Glasgow University in the bursary scheme to study modern languages and moral philosophy. And she eventually became a primary school teacher and infant mistress, and she was a really strong advocate of me getting a good education. She instilled a real discipline of study in me, and also made me think about new ways to deal with problems if things didn't quite work out. So I went to our local primary school, Spring Hill Primary School, quite often above the snow line, and here I am with my bowl cut. And I was relatively unremarkable at primary school, but by the end of it I was picked up as having an aptitude for music, such that I actually auditioned for the Strathclyde Secondary Residential Music School, but I didn't get in because my second instrument wasn't good enough. But it is quite sobering to think back, you know, you were making career decisions at the age of 10 that really were forks in the road, and if it had gone slightly differently, I wouldn't be here today. But as it was, I got over that and went to our local high school, Barrhead High, and I hung about here in the music department. And this was actually a picture of the first prize I ever won, which was with a recorder group, and we came runner-up in the Greenock Music Festival. Now, I got over... However, I moved on and I went to our local high school, Barrhead High School, and I hung about in the music department a lot. This is actually a picture of the first prize I think I ever won. We were runner-up with this recorder group in the Greenock Music Festival. That was a little taste of success. But my focus started to change around year 3 when I studied chemistry subjects. But my focus started to change around about year 3 when I started to study science, and I particularly enjoyed chemistry. And it was here I encountered my first ever inspirational teacher, Mr. Renfrew, and he just taught chemistry in the way that I understood, and I really loved the topic. He also taught me about this instrument, a mass spectrometer, and while I'm going to go on to tell you more about this, little did I know at that age that this was going to become such an important part of my career. When I finished high school, I knew I wanted to study applied chemistry, and accordingly I chose to go to University of Strathclyde to study pharmacy, and that was a decision I have always been very pleased about because it allowed me to study physical sciences at the interface of clinical medicine, and being able to communicate at that interface has actually been a real strength throughout my career. I still really loved chemistry, and I particularly liked drawing out very complicated chemical diagrams, and I was drawn to natural product chemistry, which is the study of medicinal compounds that are produced by plants. And plants can make really complicated molecules, as you can see here, such that these molecules are actually almost impossible sometimes to make in test tubes, but they have particular proteins that are within them that are called enzymes, and they can make these very specific changes to molecules so that you can construct very particular chemicals. And more than just the composition, they can make the right 3D structure. So in the same way as you've got a left shoe and a right shoe, chemical compounds can be the same. They can have two different orientations, and you need the right orientation to get activity. I was fortunate to do an undergraduate vacation scholarship in year 3, and here I met Dave Watson, who was a postdoc in the lab at the time. And I was fortunate to be able to do an undergraduate summer studentship with my personal tutor, John Midgley, who sadly died last year. And it was here I met Dave Watson, who was a postdoc in the lab at the time. Dave taught me all of my wet lab science, and I'm forever grateful, and indeed I've been very fortunate to be able to work with him continuously throughout my career. Finishing that, I knew I wanted to do a PhD, but being a pharmacist I had to first finish my professional registration, and during that year I also applied for PhD studentships, and I had to go to get interviewed by the Royal Pharmacy. So that experience allowed me to know I wanted to be this experience convinced me I wanted to study for a PhD. But being a pharmacist, that experience, having that experience let me know I wanted to go on and study for a PhD. But being a pharmacist, I had to first finish my professional registration, and then I returned to Strathclyde to study with Dave and Professor Midgley. I was funded by the Royal Pharmaceutical Society, and I had to go to London for an interview, which was extremely exciting for me because at the age of 21 I hadn't actually been to London, so I had to go up really early on the train, go down, have my interview, and I walked absolutely everywhere. I think I was actually probably just terrified to go on the tube. But it all went well and I came back with my scholarship. I was also co-funded by industry, which is one of the earlier, what we now call case studentships, and it was a company called RP Scherer. I didn't spend time in industry, but my industrial supervisor came to see me, and I particularly remember getting grilled on the quality control of my work. And I remember getting asked whether if I wrote down my method, could somebody follow it well enough so that they would come out with exactly the same product. And those were values that were very much embedded in industry at that time, but probably less so in academia. And I'm actually very pleased to say that in my lab now we have those quality control aspects embedded, and indeed that helps us work with industry and allows us to participate well in clinical trials. So I studied mass spectrometry as my PhD, and I need to tell you now what that is. So here's my original diagram, and below here's me scribbling as a PhD student trying to learn more detail about this technique. Mass spectrometers measure mass, and to all intents and purposes for today that's the same as the weight of a molecule. And a molecule is made up of atoms like carbon or hydrogen or oxygen, and each atom has a particular structure, has a central part called the nucleus, and within it we have positive components called protons and some packing material called neutrons. Surrounding the nucleus we have an orbital containing electrons that are negative. So an atom has an equal number of positive and negative charges and is neutral. However, we can change atoms into what we call ions, where we either lose or gain an electron. If we lose an electron, the molecule becomes more positive, and if we gain an electron, the molecule becomes more negative. So this is like the poles in a magnet, poles in a battery. So this is like the poles in a battery. The value of having molecules in positive or negative form is that once you've done this, you can make them move. So two positives repel from each other, two negatives repel from each other, and a positive and negative attract. It's a bit like the poles of a magnet. And that's what we do in a mass spectrometer. We take our molecules, we turn them into ions, and then we put them in some sort of force field. And there we give them a shove. And lighter molecules will move further than heavier molecules if you give them the same size of a shove. And the difference in this deflection can be measured and lets you tell the difference in mass. Now you might think you know nothing about mass spectrometry, but believe me, you have encountered it. So if you watch CSI, they frequently mass spec it. if you watch Silent Witness, Amelia Fox is always using mass spectrometry to work out what killed the body. And more recently, the UK has had a huge investment in mass spectrometry infrastructure in support of the London Olympics, because this is a type of approach that we use to measure drugs of abuse in urine from athletes. So here I am with my first mass spectrometer. It looks really old, but at the time it was absolutely cutting edge. It was a huge instrument. This part here that looks a bit like a porthole had a glass panel on the top, and if you stood on a stool you could look down and imagine you could see the ions. So it was really very large, but we got really good data from it. My PhD studied hormones. Hormones are molecules that signal within the body to tell the body what one organ is doing. So during my PhD I studied hormones. Hormones are signalling molecules in the body, and they're released by one organ system and communicate through the blood to another organ system. So for example, the gut might tell the brain it's hungry. The types of hormones I studied were formed from the adrenal glands, which are these little triangular glands that sit above the kidney. If you cut across the adrenal gland, just like cutting across an orange, you find different layers. And within those different layers you get hormones produced, and the hormones I studied were formed in the central part of the adrenal gland. This is called the adrenal medulla. So these types of hormones are hormones like adrenaline. There are hormones that allow us to respond to frightening situations, or fear, fright and flight responses, and let us cope under those in those environments. During my PhD, I studied adrenaline and related hormones in a variety of different disease states, and in order to do so, I had to work out ways that I could measure these molecules in urine. So adrenaline is formed through a series of steps, starting with L-tyrosine. L-tyrosine is a type of molecule called an amino acid, and you eat it in your diets, in like chicken and pumpkin seeds, etc. It's converted through to adrenaline through these 4 steps, and each of these steps is catalyzed and enabled by an enzyme depicted by the coloured asterisk. So there's a different enzyme each step, and it carries out a very specific change in the chemical structure. So you can see here, for example, going between L-tyrosine and L-dopa, we get an extra one of these groups added on. It's called a hydroxyl. It's an oxygen and a hydrogen. At this point you've got a change in the molecule here that makes it into dopamine, etc., etc. And I just want to draw your attention to this wedge-shaped unit here. This is called a bond, and it's the way this wedge is the way that chemists can depict 3D structure on a page. So this wedge tells me that that particular group is projecting out of the page and towards me. So I needed to measure all these molecules in urine, and if I were in Silent Witness, I'd just pick the urine up and put it in the mass spectrometer. But quite frankly, that's not how it works. We have to clean up the sample a bit before we do it, because it's way too complicated. Urine's got many multitudes of molecules within it, so you're essentially looking for a needle in a haystack. So analytical chemists like to make things a bit simpler, and let me put that in context of making a tart tatin. So if you want a tart tatin, you're going to go to the fruit market to find your Braeburn apples, and you get met by a mountain of food, all mixed up, fruit, every type of fruit imaginable. And there's a fairly good chance you'll pick up the wrong type of apple, and actually it might be quite hard to find the apples at all. So one approach to doing this is to take all the fruit, sort it all out, and perhaps divide it into citrus fruit or bananas and apples, and once you've got just the apples, you've then got a really good chance of finding the type of apple that you want. So this is what we do in analytical chemistry. We take our urine sample and divide it into the subgroups of molecules, and then we can find the molecules we want. And we do this using a technique called chromatography. So anyone who has done science at school has likely done this experiment, where if you take different colours of ink, put it on chromatography paper and dip it into alcohol or water, what happens is the molecules start to spread out. So you can see this red ink, for example, has actually got a yellow component and a red component. So if I'm only interested in the yellow components, then it's much easier for me to find them. And I can just take that yellow subset and put it into the mass spectrometer. So during my PhD, I devised ways to use chromatography to measure these molecules like adrenaline. And I used a technique called gas-liquid partition chromatography. And here you've got the diagram of the very first version of this instrument from the 1950s that was used to patent the equipment. And the group here went on to win a Nobel Prize. And essentially the system hasn't changed very much at all over the years. What we have is a syringe, and within the syringe we put our biological sample. We then inject our sample into an injector, which then holds the sample in liquid form. So it's a bit like a holding pen before a racetrack. Attached to the injector is a column, and here we have a column. It's long and it's narrow, it can be up to 50 metres long, and at all times there's a gas flowing down it. To start with, the molecules are in liquid form at the start of the column, but what we do is we heat the column up, and once we do that, molecules then will boil and pass into the gas phase. So at a particular temperature, the red molecules here, for example, pass into the gas phase and then are blown down the column. If we raise the temperature, the yellow molecules start to move, and then finally the purple ones. And so you've spread them out, and we can put them into the mass spectrometer and measure them all individually. So I developed methods with my adrenaline-like molecules to measure and spread out the compounds within the urine samples. Now, I don't have time today to tell you about all the studies in my PhD, but I'm going to just tell you one story about Parkinson's disease. Parkinson's disease is a mobility disorder. People have trouble initiating movement. They often have a tremor and they're unsteady. And this is because they can't make dopamine in certain parts of the brain. And one of the ways we treat this is by trying to replace that dopamine in the brain by giving a precursor called L-DOPA, and it's levodopa tablet. My PhD studied what happens to that levodopa particle, that levodopa tablet, because we know that although we can replace dopamine, it's not a perfect solution. People still have side effects, the effects wear off, and some people react badly. So what I found was when you gave levodopa in a tablet rather than by making it yourself, that the dopamine formed got converted through to a set of molecules that actually were damaging to the nerves. So this dopamine got converted into what we call hydroxydopamine. Another hydroxyl group got put on at one of these starred positions. And these are very reactive molecules. They're described as oxidative. They can damage membranes. And here you can see them in a urine sample, and I was able to show that people with Parkinson's disease had a tendency to form these anyway, but in low amounts. But if you treated them with levodopa, they formed very large amounts. You can see these very large peaks here, which I was able to identify with a mass spectrometer as these hydroxydopamines. So essentially, although we're doing some benefit, we're also doing some harm. And this is the first paper I ever published, which is very exciting as a young scientist. I looked back when I was preparing this talk about how I collated that data, and I was able to find my lab books where I was actually drawing out the chromatograms. So this was way before the days of Windows as we know it now. It was Windows 3.1, dot matrix printers. We couldn't just take a photo on our mobile phones. But it's really important as a scientist to take rigorous notes, and that still stands today, even though we're a little bit more electronically enabled. So I finished my PhD and I knew I wanted to continue, and I hopped on the train and came to the University of Edinburgh and was met by this rather intimidating interview panel, two of whom are here today. This team advertised a job because they had funding from the Wellcome Trust to study hormones in urine. It was a different type of hormone, it was steroid hormones, but likewise they wanted to use mass spectrometry, so that fitted well with my skills. Now, steroid hormones are also formed in the adrenal gland, but in a different zone, a slightly more exterior zone called the adrenal cortex, and they've got a slightly different chemical structure. And they too help us deal with stress, but maybe just over a slightly longer time frame. So the steroid hormones I studied the main one was called cortisol, and it's one of a family called glucocorticoids, and to some extent the clue of what they do is in the name. It helps us control our glucose levels. So it helps us manage our fuel when we need it, it helps us cope with stress, and it helps us manage inflammation, and also controls our blood pressure. So again, it helps us cope with the ups and downs of daily life. And probably most recently you might have heard of this group of hormones because dexamethasone that's been talked about with treating COVID-19 is one of these glucocorticoid hormones, just one that's made synthetically, and it controlled inflammation in this setting. So it's important to recognise that glucocorticoids have to be very tightly controlled in the body. If you have too much of them, you start to bring about diseases like diabetes, mental illness, immune suppression and high blood pressure. So the control of cortisol levels is very important. So the team I was working with wanted to study one of the control mechanisms for cortisol and how it managed high blood pressure. And they were interested in a particular enzyme which existed in the kidney, and it turned cortisol into an inactive form. So the enzyme was called 11-beta hydroxysteroid dehydrogenase type 2, or 11-beta HSD2, and I'm only going to say that once. So it caused a small change to the molecule shape. You can see the hydroxyl going to what we call a ketone, and this was enough to inactivate the cortisol. So therefore this mechanism controlled the levels of cortisol in the kidney, and it was thought if the kidney got exposed to too much cortisol, you could bring about high blood pressure. So how does this little chemical change happen? Well, cortisol has to interact with what we call a protein called a receptor to affect its actions. Here's the receptor here. You can see it's quite a complicated shape. And the cortisol has to land on it in exactly the right way, which is dependent on its 3D structure. So it's a bit like landing on the moon. The moon landing has to put down, the shuttle has to put down its feet properly, not land on a rock. So the little change that you've got between cortisol and cortisone is enough to stop the cortisone binding. If you look at the structure of cortisol, you can see it's got a flat plane, and it's also got another plane where little spokes poke out. So it has to land with a flat plane onto the receptor. So what this research project looked at was whether there are people in the population that were less able to inactivate cortisol and thus more prone to having high blood pressure due to cortisol excess in the kidney. And there are various ways this could happen. So for example, if you take licorice, that can actually stop this enzyme working properly. But also more likely it's people with subtle changes in their genetic code that make the enzyme more or less effective. So we studied this across a range of people in the population to find out what the range of responses could be. So to do this, to measure this, I had to set up ways to measure cortisol and cortisone in urine. And I was given my own mass spectrometer, which might sound like the biggest Christmas present you've ever had in your life, but it was actually frankly terrifying. Because I had just come from being a student, and as a student you're so well supported by your supervisor, your technical team, your technologists, and whenever the instrument stops working, they all come forward and help you fix it. The student generally doesn't do the troubleshooting and maintenance. In fact, mass spectrometers are really complicated, complex, sophisticated instruments. They're a bit like performance sports cars, and you simply don't let the students near the V8 engine. So they take a pit stop and the team come out and help. But you know, this was really quite an obstacle to me, and I think it's important to recognise you're going to encounter obstacles in your career, and if you want to succeed, you've got to get past them, round them, under them, over them. Some way you've got to get beyond them. And it's at these times you realise the importance of friends. And I was very fortunate to be able to reach out to some friends who could help me get out the starting blocks here. And more recently I've been really happy to be one of the co-founders of the Scottish Metabolomics Network, which is a network of mass spec experts across Scotland, and indeed we do phone a friend in situations like this. So I managed to make the instrument work and measure cortisol and cortisone, and by about the summer I was starting to get data. So here we have one of our chromatograms for steroids in urine. I was able to take the steroid sample. I'd worked out my clean-up method so I could separate my apples from my pears, and then I could measure various compounds in the urine samples. And cortisol and cortisone are two of the peaks in this printout. This then reached the point that it got really exciting, because instead of just doing this using standard chemicals in the lab, you could start to measure what was actually happening in real people. And a common approach that scientists take when they're looking for subtle differences, if they want to prove their approach works, is you usually look at an extreme situation first. So we were fortunate that the team I was working with had a patient who they believed had a dysfunctional enzyme. So they had a really severe mutation in the enzyme, And accordingly, they expected this patient not to be able to convert cortisol to cortisone at all, and indeed they had very high blood pressure. So it was a very exciting day, the day I was able to actually run the urine sample from this patient and show that for sure they did have an extremely large peak of cortisol and virtually nothing for cortisone. Indeed, you're just looking at like grass, long grass here. So that led to some very exciting studies studying the ability of this enzyme to inactivate cortisol in very many populations around the world with varying degrees of problems with blood pressure. Very quickly then we started to expand. We wanted to measure other types of biological samples like blood or hair or saliva, and by the Christmas I can see I was measuring some early studies in by Christmas. Very quickly we wanted to move on to measure in other types of biological fluids like blood and hair and saliva, and by Christmas I was starting to measure it in plasma samples of some dude called Brian, who of course is Brian Walker, who is has been one of my mentors. And I think it's really very important to mention the importance of working with people who guide you through your career, both telling you the things that you want to hear and sometimes the things you don't want to hear, and for that I owe Brian a debt of gratitude. So together we've studied cortisol and its metabolism in samples in populations all around the world. This is a map of where all the collaborations we've had. I realise we haven't worked yet in Australia, so I must fix that, but this has led to some very exciting studies in a variety of settings. We've studied stress hormones in babies, in pregnancy, with different dietary impacts, with season, with stressful events like the Holocaust and September 11th, and across different organ systems where disease might happen. Quite a lot of our work's been done in diabetes, obesity, and in later life Alzheimer's, and many of these studies have also included collaborations with Jonathan Seckle and Rebecca Reynolds. I've also been lucky to work with an absolute Noah's Ark worth of animals, and indeed we actually were involved with some of the reproductive hormone profiling of the Edinburgh panda. So the next step in my career was to get a tenured lectureship, and at this point it's quite important to be able to articulate what your unique niche is. What are you independently going to bring to the world of academia? And for me that became using mass spectrometry to really address questions that had been previously unattainable in steroid hormone biology. And just going to give you an example of a few. So I've shown you this system that the adrenal gland produces cortisol, it can get inactivated by the kidney, and then turned into cortisone. But the situation is a little bit more complex than that, in that in the late 90s we discovered there was a second enzyme that converted cortisol back from cortisone, so you could regenerate active cortisol in certain tissues like liver. But the situation became a little bit more complicated in the 90s, because a second enzyme, this type 1 enzyme, was identified which took cortisone and converted it back to cortisol, and this would happen in tissues like liver or fat or brain. And that meant that if you measured cortisol in blood, you really didn't know where it was coming from, so it really added quite a layer of confusion to interpreting blood samples. So I devised ways that we could map this particular activation pathway by doing a technique called stable isotope labeling. So stable isotope labeling involves adding tags onto the molecule called stable isotopes that you can measure in the mass spectrometer. Now, if I just returned my initial images of atoms, you can see that cortisol has a lot of these hydrogen atoms in it, and they normally have a proton and one electron. But you get some less common versions of hydrogen which also have one of these packing material units called neutrons, and this is termed a deuterium molecule. And the thing about a deuterium molecule, it weighs 1 mass unit more than the natural hydrogen, and the mass spectrometer can detect it. So I was able to put deuteriums onto the cortisol molecule, and from that we would add 3 onto cortisone. So I was able to add deuteriums onto the cortisone molecule such that when cortisol was formed by this additional enzyme, the cortisol had 3 deuteriums on it, and we were able to therefore distinguish that from the cortisol that was formed from the adrenal glands, and that has allowed us to work out how much of our cortisol load is coming from tissues like fat or liver and brain, and how indeed this changes in disease. And we've studied each of these individual organs by measuring the blood that goes into them and comes out of them, and really these very complex clinical setups. Now, I've been lucky to work with very many talented clinical fellows who've enabled this. I mean, most recently we've shown that actually fat forms quite a large amount of the excess cortisol that enters the blood. So therefore, if you want to dampen down cortisol, and we've been involved with developing drugs in this field, then I've forgotten. So this enzyme now has become quite an attractive drug target, because you can lower the levels of cortisol in your fat tissues or in your liver or in your brain, and that's beneficial for reducing your risk of diabetes or indeed cognitive decline. That's aging and loss of memory with aging. So this enzyme has become an attractive drug target, because you can stop it working, you can reduce the amount of cortisol in tissues like liver or adipose fat tissues or brain, and that can reduce your risk of diabetes or indeed of decline in brain health with aging. And I've been really lucky to work alongside our drug development chemists such as Scott Webster in part of the clinical trials that are evaluating these types of drugs. We've also managed to study all these different organs individually. We've measured the glucocorticoids in the blood entering the organ, like the liver, and the steroid in the blood that comes out of the tissue as well. And therefore we can tell how all these individual organs contribute to the whole body load of cortisol. And indeed, most recently we've shown that the fat tissue generates a lot of cortisol, and it spills over a lot into the blood. So the next story I'm going to tell you relates to just, I guess, serendipity and the powers of observation in science, because there's often more to see in your data than you're expecting. So I showed you earlier we were working on our cortisol and cortisone conversions, and we generated our chromatograms with the steroids, and you can see there are more peaks than just the two steroids that I'm talking about. And within these, my attention was drawn to another couple of molecules called 5-beta and 5-alpha tetrahydrocortisol. So tetrahydro just means there's 4 extra hydrogens, and there's 2 types of these. And what I noticed was that in people who had lean bodies, they formed more of the 5-beta version, and in people that were fat, they formed more of the 5-alpha version. And I really didn't know if this was important or not, but it was definitely consistent across quite a large number of people we studied. So let me tell you what the difference is between an alpha and beta steroid. What do I mean? Well, you can see the 5 positions here, and the alpha has got a dashed bond, whereas the beta has got one of these wedge bonds. So that hydrogen's coming out the screen towards us, whereas the alpha one is projecting away from the screen. And if you look at that in 3D, you can see that the alpha steroid is relatively flat. It's quite like the original glucocorticoid I showed you, but the beta steroid is completely different shape. So just the change of that hydrogen means that you've got a very skewed molecule. So this is really quite unlikely to work in the same way as the alpha one. So this led me to think maybe there's another enzyme of interest, and this enzyme is called 5-alpha reductase, and there are 2 of them. So we knew, therefore, in people as they got increasingly more fat, they formed more of the 5-alpha tetrahydrocortisol, but we didn't know what this meant. There's various explanations. It could be that the 5-alpha compound was bad for you in promoting obesity, but we thought it was maybe more likely actually this was a way that the body was getting rid of cortisol, because we knew that cortisol in itself was bad for you. Cortisol would cause obesity and diabetes, so therefore it might well be that the body was trying to rid itself of something, and that was why we're forming more. So the way that scientists usually approach this type of system, if you don't know what something's doing, is that you would actually study a system where you take the enzymes out of the equation. So you remove the 5-alpha reductases and see what happens. You would assume these people would accumulate extra cortisol and become worse off. So we studied this first in animals, where we were able to genetically modify the DNA in mice to remove the 5-alpha reductase enzymes. And this is work of Don Livingston. So these mice are called knockout mice, and we studied them on a high-fat diet over a period of half a year. And you could see in the open triangles that the mice that lacked the enzyme had a much greater gain in weight. And indeed they put on a lot more fat. You can see it with your eyes, and you can also do scans in mice that are very similar to what we do in humans, where we can see in white here the fat accumulation in the mice. We also were able to show these mice were starting to not control their insulin levels properly, and they were putting fat in places in their body where they shouldn't be, like the liver. So these are big red blobs are liver fat, so that's bad news as well. So overall these animals looked like they were heading towards developing diabetes. We went on to study this further in the human setting, and we were able So does this matter in humans then? Well, yes, it does, because although you don't get very many humans with genetic modifications of 5-alpha reductase, you do get a lot of people taking drugs that inhibit 5-alpha reductase, which is essentially going to lead to the same problem. Now, the reason people take these drugs is actually to treat prostate disease. So 5-alpha reductases have more than one role in the body. They also are important with converting testosterone to another type of molecule, to another type of androgen. So testosterone is the major sex steroid in males. It's called an androgen, and most people associate that as being the main sex hormone in the man. However, it's actually activated. It's actually They were also starting to not control their insulin properly, and they were putting fat in places of the body that wasn't good news, that it was bad for them. So these are actually sections of liver, and you can see with the red dots big blobs of fat accumulating in the liver, which I say it's not good for your health. So overall these mice looked like they were progressing towards diabetes, and we wanted therefore to see whether or not this was relevant to man. So it suggests that indeed the 5-alpha reductase enzymes are protecting the body by removing the glucocorticoid. So does this matter in man? Well, you don't get that many men with or women with. So does this matter in humans? Well, yes, it does. You don't get that many people with genetic modifications in 5-alpha reductase. It's pretty rare. However, there's a very large number of men in particular that take drugs that stop 5-alpha reductases working, and these are men that have got prostate disease. So 5-alpha reductases have more than one function, and they're also involved with the control of testosterone action. So testosterone is the androgen that most people associate with the male sex characteristics, but actually it gets changed by 5-alpha reductases into a more active version called 5-alpha dihydrotestosterone. And this happens in tissues in the body where you want to amplify the role of androgens, such as the prostate gland. So the prostate gland with age in men tends to swell, and this is in response to androgen levels. When it swells, it presses on the ureter and it stops urine passing freely, and it's painful. So this is a disease that happens quite commonly in men. About 80% of men over the age of 80 have it. And it's treated by reducing the action of androgens on the prostate. And you do this, for example, by giving drugs that stop 5-alpha reductase acting. So that dampens down this very active androgen. However, our hypothesis was that if you did this, you were also interfering with glucocorticoid biology, and you could be exposing people, like our mice, to developing diabetes. So we studied this in the general population, looking at prescription records of people that were receiving these drugs to see whether or not they were more likely to develop type 2 diabetes. This is adult onset diabetes. Now, we're very fortunate in Scotland because we've got very good prescription records and we can track people like this in an anonymous manner. So we were able to collect all the data, clean up the data, tidy it up and make sure we had it correct, and divide it into groups of people that were receiving the 5-alpha reductase inhibitors, and there are 2 drugs named here that are such drugs, and compare them to a control group of subjects that weren't taking the drugs. And we do a number of types of data tidying in this setting. We adjust for confounders. What we mean by that is we might adjust for whether people make sure that all the groups have got the same range of weights or ages, and we also control for their GP practice so that we've got some control over their societal and lifestyle factors. And we were able to show that people receiving these drugs actually had a 30% greater chance of developing diabetes. And more so, this was more likely to affect you if you were overweight. The people that were in the lean sort of body mass indexes were less affected. So this has been quite important work that's brought about a new risk factor for type 2 diabetes, and indeed is getting surveillance at the European level, just to see if there's something that we need to do to intervene to help with the health of these people when they receive these drugs for their prostate disease, which can be a very important treatment. Now, my last story is to tell you a little bit more about another mass spectrometry innovation I've worked with more recently. And I'm going to go back to my original experiment again, looking at cortisol going to cortisone in urine. We were interested to know the control of this enzyme that protected the kidney from the excess cortisol. And we were able to measure it originally in urine, but if that didn't tell us a lot about what was actually happening in the kidney, because if you look at the structure of the kidney, so I'm going to go, my last story today is to tell you a little bit more about a newer technique I've been using in mass spectrometry to further understand more about steroid hormone biology. And I'll go back to my original experiment where we were studying cortisol getting converted to cortisone in the kidney by this enzyme 11-beta-hydroxysteroid dehydrogenase type 2. And for those early studies we used urine, which gives us the total output of the kidney. And it's an excellent matrix to use in the clinic because it's easily collected, it's non-invasive. But it gives you a holistic view of the kidney. And if you just look at this picture that I have of the kidney, you can see there's a lot of fine structure. The kidney is composed of tubes called nephrons, and they zigzag across the kidney. And along these tubes there are different zones where there are different functions. So, for example, there's an area where we control glucose, there's an area where we control sodium, potassium, water, etc. And all these functions matter. We believed that cortisol was interfering with sodium transport, but you couldn't tell that by just measuring it in a urine sample. You needed to find out what the actual cortisol levels was at each of the different points along this tube. So more recently we've been trying to do that, and for that I'm using a technique called mass spectrometry imaging. So this is a technique that allows you to measure in biopsies. So you can take biopsy and take a section of it and try to capture the molecules in the different histological zones. We use a laser. I get to work with lasers and fire them, and we fire them at the tissue in a grid pattern, and from that we collect all the different molecules in each of the laser bores. They get sent to the mass spectrometer and they get the molecules within those bores get measured. Now we don't have any chromatography in this setting, so we have to use a very advanced type of mass spectrometry that separates the molecules by spinning them. The lighter molecules spin more rapidly than the heavy ones, and we use mathematical deconvolution to tell the mass to a really very specific degree. And from that we can then map molecules. So here we are mapping the active glucocorticoid versus the inactive glucocorticoid in the kidney. And you can see from this heat map that this zone here has got a higher level of cortisol, so therefore that particular part of the kidney and whatever functions are happening is seeing the cortisol, whereas this zone here has got much more inactive levels, and therefore that is protected from glucocorticoids. So that starts to tell us about what cortisol is doing and where it's acting in the kidney. And indeed you can measure very many molecules. Within our data sets we have lots of known molecules, and we look to see where they are. Sometimes they're places we expect them to be, sometimes they're somewhere else completely else. Sometimes molecules are where we expect them to be, sometimes they're not. We also find unknown molecules we've not weren't expecting to see in places that are maybe very relevant for disease. So this technique's been it's been fascinating to work with, because once we have these maps we can then superimpose them all together to find which molecules are in the same part of the tissue. So you can find molecular neighbourhoods and networks, you know, whether molecules are living in the same house or over the garden fence, and that allows us now to look in, actually we're doing this in 3D, how molecules interact at the tissue surface, and this brings much more information about how biology functions. So we've been developing this technique really actively over the last few years, and I particularly want to mention Shazia Khan here, who's been on this journey with me developing our abilities. We've studied lung disease, steroids and aging, recovering from heart attacks. This is drugs in myocardium, in scars following a heart attack, in lipids in atherosclerosis, looking at the plaques, fertility, wound healing. Here we have the surface of the skin with steroids. We also have looked at zebrafish and other animal models, and so we've been developing this technique very actively over the last few years, and I just particularly want to mention Shazia Khan here, who's been pivotal in developing this work alongside me for the last about 10 years. We've studied steroids and lung disease, we've looked in aging, we've looked at patients recovering from heart attacks, models of atherosclerosis with plaques, fertility. Here's the surface of the skin with steroids penetrating, drug delivery programs, and some model organisms as well as zebrafish. So it's a fascinating technique. But you know, so what next? So the next field that I'm going to work so mass spectrometry has evolved hugely in the time I've been working my way through my career, and it still continues to do so. So the very next mass spectrometry has evolved hugely in the time I've worked in it, from my very first initial instrument, and it continues to do so. And the next approach that we're taking is now we're wanting to measure shape directly. I've been telling you all along that shape really matters for biological compounds. Here's our alpha and beta. And now mass spectrometers can actually measure shape. They measure the space a molecule takes up in 3D. And if you have two molecules that have got the same mass, but different shape, one's more folded, then they travel through space at a different time, and mass spectrometers can now measure that and relate it to differences in shape to the angstrom level. So these are very exciting new techniques, and we also have methods that we can model this and predict what will happen by looking at squeezing and shaping and stretching the molecule. We also have methods that we can predict this now by stretching and squeezing the molecule to find its most stable conformation. So there's plenty new approaches we have available now in steroid biochemistry, and I intend to continue exploring them. I wanted to just mention another few things that I've been involved with in my career that have been important to me. When you develop your career, as I have done as at the interface of technology, what you find is when you give a talk like this, people get really excited about your work because they can see the parallels with their own research questions, and they want to apply what you've done to their work. And that can lead to a huge number of stimulating conversations and exciting ideas. But in the long run, you become your own worst limitation, because there's only one of you and one pair of hands in 24 hours in the day. So it can be very difficult to help people, even though you can see these exciting possibilities. So I was very lucky to be able to develop the Edinburgh Mass Spectrometry core, because the Wellcome Trust invested in clinical research facilities in the late 90s, because they recognised that to fully embrace the opportunities of technologies, you needed to make them available to a wider group of scientists and not just the experts. And for that, they invested in technology hubs, and we were one of the first to receive funding in Edinburgh to develop our mass spectrometry core. And I'd just like to mention Natalie here, who came in right at the start of this and has worked alongside me in building up our core facility. And she's very much well recognised now for enabling other researchers to access mass spectrometry for their purposes, and I think we've matured together. We're a much larger group now. We've come a huge way from my one instrument and my manual syringe. We're fully automated and able to do high throughput, and we're now a team of 7 with about 6 to 7 instruments. So this has been a huge success and a great pleasure. The route of careers for expert technologists is still a tricky one, and it's a new career. The career path of expert technologists is still a new one in Edinburgh University. The career path of expert technologists is still a new one, but an area I believe we have to invest in to fully capture the opportunities of scientific infrastructure. I just wanted to share with you this graph to highlight some of the other roles that the modern academic has to carry out. This was a graph that Natalie and I developed for one of our recent funding applications about a year ago, and it shows the evolution of the mass spectrometry core, where it's grown in its turnover by at least tenfold. We're now routinely coping with 6-figure turnovers per annum. So we need to be very good at finance and have an ability to manage budgets. We've also expanded our team from just initially just us to our team of 7. So for that we need to be watching people's careers and able to help them develop, along with the ups and downs of personnel management. We've also expanded our teams from 2 up to 7, so that brings with the responsibilities of managing people's careers, coping with the ups and downs of careers throughout life. We have to sustain and maintain our instruments with an eye to the environment, and we also have to regularly try to be horizon scanning to bring in new exciting infrastructure into Edinburgh, and that involves both writing grant applications but doing Dragon's Den pitches for funding. So academic careers are very varied and challenging, but I think there are maybe some business skills embedded in here that are perhaps not immediately obvious. My last area to talk about is teaching about hormones. I've been telling you today about research, but I very much enjoy teaching with hormones, and so the last area I wanted to talk about is teaching about hormones. One of the most satisfying areas of my career is seeing my students develop and go on and develop their own careers and their own interests. And that starts with undergraduates, and I've very much enjoyed developing courses to teach about hormone science in undergraduate biomedical sciences. I particularly like working with the fourth year honours students because they're at the point in their career where they're just moving away from the textbook and starting to realise knowledge is unstable, and more than that, they can contribute to the future, so that's quite a creative time for them, and I find that a particularly rewarding phase. The other thing I enjoy about teaching is its collegiality, and I think that was never more so evident other than during the pandemic, when we had to work so closely with our colleagues to deliver and maintain high quality education. Research by its nature is competitive. Lastly, I want to talk about teaching about hormones. One of the most satisfying things is working with your students and seeing them develop and progress to their own careers with their own interests, and that starts with undergraduates, and I've really enjoyed developing courses for undergraduates to study hormone science. I particularly like working with fourth year students. This is the point when they're moving away from working in textbooks to realising knowledge is uncertain and evolving, and actually more so they can contribute to the future. So it's a very creative time. And the other thing I like about teaching is its collegiality. Research by its nature is competitive, but teaching to me is an enormous team effort, and I think that was never more obvious than during the pandemic, when we had to pull together very strongly with our team to maintain high quality education. I've enjoyed the other thing I enjoy about teaching is the collegiality. Research by its nature is competitive, but to me teaching is a huge team effort, and I think that was never the more obvious. As the other thing I enjoy about teaching is its collegiality. Research by its nature is competitive, but for me teaching is a huge team effort, and that was never the more so obvious than during the pandemic, when we really had to pull together to deliver and maintain high quality education in the face of a lot of challenges. And I know my fourth year honours project is in excellent hands of my colleagues here. And I know my fourth year honours course is now in the excellent hands of Don Livingston moving forward. The other thing I enjoy about teaching is its collegiality. Research by its nature is competitive, but teaching to me is a huge team effort to deliver a course, and I think that was never the more so obvious as during the pandemic, when we really had to pull together to maintain a high quality education online. I'm a strong believer in postgraduate education in higher education, and I was one of the early cohorts to study for a postgraduate certificate because I was interested in learning about digital education. And I'm actually very proud that my enthusiasm for this has rubbed off in many of my team, and hopefully, Shazia, I will be joining this group of graduates in the near future. So everything I've told you today has been teamwork, and there's been an enormous number of students and postdocs and colleagues that I've worked with, and I'm really proud to see them progress, and some of them still are with me. But I think the people on the far side are the ones that deserve some special mention. The group on the top are my mentors, those that helped me and guided me, told me what I wanted to hear and didn't want to hear, and all throughout my career, and for which I'm very grateful. The group in the middle are my colleagues that have grown old with me, but these are really important. The group on the group at the top are my mentors that have helped me from PhD, as Dave and John Midgley. The group at the top are my mentors, Dave, Professor Midgley, Jonathan, Brian, Chris, Mandy. They guided me through my career. They've been just a little bit ahead of me in that Group in the top are those who have been my mentors. They were just a bit ahead of me in their careers and were able to guide me and say, sometimes telling me things I didn't want to hear, but always having my best interests at heart. The group in the middle are colleagues that I've matured with, and these are really important people because you can discuss the current challenges that we're all facing as we go through our careers. And lastly, Dawn and Natalie, who started working in my group but have become very valuable colleagues with their own highly successful careers. Of course, there's life beyond work, and for that I thank my partner Roger, who's always there to support me. During COVID, when I decided to upskill in cookery, he supportively ate everything, and he's always there in the first row of my concerts because I haven't forgotten music. And I think in days, I've told you, but of course there's life beyond work, and I wouldn't be the same without my partner Roger, who's always there to support me. During COVID, when I decided to upskill in cookery, he supportively ate everything and he's always in the front row of my concerts because I haven't forgotten music. I've told you about the peaks of my career today, but there are days when there are troughs, and in those days it's important to be able to go somewhere else in your life where you can be happy, relax and regenerate. And for that, I think but of course there's always life beyond work, and it wouldn't be of course there's life beyond work, and for that I'm grateful to my partner Roger. We've travelled the world together and he's always there to support me. When I decided to upskill in cookery during the COVID pandemic, he supportively ate everything, and he's always in the front row of my concerts because I haven't forgotten music. I told you about the peaks of my career today, but there are days when there are troughs, and it's really important to have somewhere else in your life to go where you can just relax and be happy and regenerate. So lastly, just thank you to everyone who's come to listen, and thank you to all my sponsors, and I hope you found that interesting.